built a toy box for his son. Ryan definitely wants it to be a triangular sandbox, so I've given you the illustration. How much wood would it require to make the outside of the box? Let's answer that question first. In order to make the outside of the box, we're looking for the perimeter, which is going to constitute side 1 plus side 2 plus side 3. Well, right now we're only given one side of the box, and we can't just randomly guess the values of the other. But I do notice that we have a 30-degree symbol here, and we have a 90-degree symbol there, which means this other angle must be 60 degrees, using our triangle sum theorem to realize, hey, 3 angles in a triangle add up to 180. 30 plus 60 is 90, plus 90 is 180. Now, we also learned 2 weeks ago that there was a special relationship between 30, 60, 90 triangles. And that relationship was x root 3, 2x. Now, notice that across from the 90-degree angle is the side that is 2x. So across from the 90-degree angle is the side that is 2x, which means this side is 2x, but it's also 6 feet. Well, if something is 2x but also 6 feet, that means we can set those statements equal to each other. 2x is equal to 6. Divide by 2 on both sides, and x is equal to 3. All right. Now, the side across from the 30-degree angle we said was the x value, and we just identified a value of x to be 3. We're doing pretty good. We've now cleared out 2 of our sides. We just need to find the missing third one. All right. The angle across from the side across from the 60-degree angle we determined was x root 3, and we now know the value of x. So my missing side down here must be 3 root 3. So we have a perimeter that is equal to 6 feet plus 3 feet plus 3 root 3. Please be careful when combining like terms. Notice 3 root 3 is not a like term to the 6 and the 3. 3 root 3 is an irrational number. 6 is rational. 3 is rational. We can combine the 2 rational terms, but we cannot combine it to an irrational term. The irrational term is functioning like a variable. So 6 plus 3 gives me 9 plus 3 root 3. Our perimeter in total is 9 plus 3 root 3. Now, you could certainly take this and make it an approximate value. So you would plug this solution into your calculator and ask for the approximate solution. But we're not going to do that right now. We're going to keep moving on to the next part of the question. How much sand would be put in the box if it's 1 foot tall? Well, if it's 1 foot tall, that means it has a base that is a triangle. So we have to be dealing with a triangular LAR prism. And since we're dealing with a triangular prism, it's going to use the volume formula. Volume is equal to big B times H, where we always want to start by finding the area of the base. So, area of the base, we need to look for the triangle's right angle because that's the one that is touching both the height and the base of the triangle. So, the base of our triangular prism is a triangle. That's going to use the formula 1/2 base times height. So 1/2 of a base, which is 3 root 3, times a height, which is 3. And we combine everything together. 1 times 3 root 3 is 3 root 3. 3 root 3 times 3. Now that time we can combine. That would be the same as me saying 3 times 3x. Or more commonly, we see this as 3 times 3x. We can combine those by multiplying. Remember that 3x times 3 is the same thing as saying 3x plus 3x plus 3x, where all three of those terms are identical. They are like terms. 3x plus 3x is 6x plus 3x is 9x, which would be the same as if we had multiplied 3 times 3 and got 9x. So we have 3 root 3 times 3 is going to be 3 times 3, which is 9 root 3. 2 times 1 is 2. All of that was our big B value. So we want to take our big B value and plug it into our original equation. Volume is equal to 9 root 3 over 2 times the height. Well, how tall is this prism? Yes, I made it easy. It's only 1 foot tall. So anything times 1 is itself. The volume itself is also then going to be 9 root 3 over 2 feet cubed. All right, today our focus is on characteristics of a function. So we have our first characteristic, linear. Notice its root word, line, versus nonlinear, which roots no line. So we're either going to have something that's a straight line or we're going to have something that's not a straight line. It's as simple as that for today. So in the linear column, we have equations that look like this. Y equals 2x plus 3, y equals 1/4 x. Now I highlighted the 1/4 x. This we should remember from last year as direct variation. Direct variation is always going to show up in the form y equals kx, where k is representing our rate of change. We're going to talk about this other form of the equation a little bit later this week, so I'll leave that for right now. Nonlinear, y equals x squared plus 3 and y equals 4x cubed. Notice the difference between the linear and nonlinear equations. The linear equations have x to the first power. The nonlinear equations have these exponential powers that are no longer 1. That's probably going to play into why they are not linear. We'll talk about that a little bit more as we move through the unit. All right, so a graph of a linear equation. Notice, straight line, arrows on both ends. This particular graph does not have direct variation. All right, nonlinear equation, not a straight line. It's going to be a curve. Now, we talked about a couple of other variations of nonlinears. Your standard quadratic is going to look like this. Your standard cubic is going to look like that. Just for kicks, we can look at your standard quartic. It's going to look something like that. And there's plenty more. You can keep adding to the power, x squared, x cubed, x to the fourth, x to the fifth, x to the sixth, and see what changes in the graph. We'll do that later in the year using some graphing software. Now, linear in a table. It's important that when we get a table, we verify that it is or is not linear. And we can do that real quick and easy by looking at our changes in our x's and our changes in our y's. So I'm going to start with the changes in the x's. 0 to 1 is a change of 1. 1 to 2 is a change of 1. 2 to 3 is a change of 1. 3 to 4 is a change of 1. Yes, we have equal intervals over here because we increase by 1 each time. Well, what about our change in our y's? 2 to 5 is a change of 3. 5 to 8 is a change of 3. 8 to 11 is a change of 3. And 11 to 14, that's also a change of 3. So our y's are increasing by 3 for each single interval of a 1 increase in the x. Another way we talk about this is k, our constant, being equal to y over x. And so we would say that our y over x is a change in a y's of 3, a change in x's of 1. All right. Nonlinear. Again, we want to check to see if it has a constant rate of change. So we want to look at our changes in our x's, our changes in our y's. So 0 to 1 is 1, 1 to 2 is 1, 2 to 3 is 1, 3 to 4 is 1. Each of those has an even increment in change. 3 to 4 is 1. 4 to 7, wait a minute, that's different. Now all of a sudden we have a change in this even increment or interval of 1 over 1, but we have a change in this interval of 3 over 1. That's not a constant rate of change, so it would not be linear. Look at the graphs real quick. Pause the video, see if you can determine which one's linear, which one's non. All right, obviously A is not linear, B is linear. All right, hopefully you determined that C is linear, D is not linear. All right, to tell whether a function in a table is linear or nonlinear, we're going to do the same thing we did with our t-charts in the previous slides. So we want to look at our changes in our x's and our changes in our y's. So 1 to 2 has a change of 1, 2 to 3 has a change of 1, 1 to 4 has a change of 3, 4 to 9 has a change of 5. So our change in one interval is 3 over 1. Our change in the other interval is 5 over 1. Those are not a constant rate of change. And thus we know we're not dealing with a linear relationship. This would be nonlinear. Go ahead and look at the following two. See if you can determine which one will be linear, which one will be nonlinear. All right. So I see a change of 1, I see a change of 1, I see a change of 2, and a change of 2. I have a constant rate of change, so it would be linear. All right, on the graph on the right, or chart on the right, we have a change of 1, a change of 1, a change of 3, a change of 6. And so we would say that is nonlinear. Tell whether the function shows a linear or nonlinear relationship. Now, right off the bat, we should see, hey, an exponential power of 2. That should be a great indicator that we're dealing with nonlinear. Now, if we needed to check it, we could certainly check it with a graph or a t-chart. So, let's start with our t-chart, plug in some x values, and see what we get. So I'm going to start by plugging a 1 into the equation. 1 minus 1 squared. Well, 1 minus 1 is 0. Squared is 0. Let's plug a 2 into the equation. 2 minus 1 squared. Well, 2 minus 1 is 1. Squared is still 1. Let's plug a 3 into the equation. 3 minus 1 squared. 3 minus 1 is 2. Squared is 4. Now, I don't know if you're noticing what I'm noticing, but I see even intervals over here and an interval change of 1 with an interval change of 3. Already, we have determined that this is not linear. Equation on the right. Our equation on the right should look really familiar to you. I mean, it starts off in y equals kx notation, but then shifted very quickly to y equals mx plus b notation, which you should have been introduced at least surface-wise to that last year in 6-7. If you don't remember, that's okay. We're going to recover it again later this week. But we can always do the same thing. We can create a t-chart where we plug in values of x and y. So I'm going to start by plugging in a 1 for x. 2 times 1 minus 4. 2 minus 4 is negative 2. All right, I'm plugging a 2. 2 times 2 minus 4. Well, 2 times 2 is 4. Minus 4 is 0. 2 times 3 minus 4. 2 times 3 is 6. Minus 4 is 2. 2 times 4 minus 4. 2 times 4 is 8. Minus 4 is 4. I'm noticing we have constant change here of 1 because we have equal intervals. I chose the equal intervals on purpose so that we wouldn't have to do a whole lot of work on that right side. On the left side, we're increasing by 2, increasing by 2, and increasing by 2. We have a constant rate of change. Independent versus dependent variables. We talked about this a little bit when we introduced domain and range. Your independent variables is all of your inputs. It's all of your x values. All of your x values constitute your domain. Your independent variable is the one that can stand alone by itself. Well, then you have dependent variables. Dependent variables are dependent upon something else. Think of yourself as a dependent. Your parents claim you as a dependent on their taxes because you depend on them to take care of yourself. Now, dependent variables are all of your outputs. It's all of your y values. And all of your y values constitute the range. So we have an independent variable, we have a dependent variable, and we have an example. Go ahead and pause the video, jot down your notes for independent, dependent, and then see if you can determine the independent and dependent variable in the example. All right, welcome back. So I always like to start with the dependent variable because I like to ask myself which variable requires something else. A painter must measure a room before deciding how much paint to buy. In order for me to know how much paint I'm going to buy, I need to know something else. I need to know the measurements of the room. So the one that's dependent is the paint, and it's dependent upon the measurement. So my paint, or how much paint I need, is going to be my dependent variable. The measurement of the room is going to be my independent variable. All right, look at the graph, see if you can identify the dependent and independent variables. Now, good math is always going to put the independent variable down here on the x-axis. That being said, you have got a lot of graphs on Google that do not have the dependent variable on the x-axis. So in order to make sure that somebody has done one right, or to make sure that it's not an assessment trying to make sure that you know which variables are dependent and independent, it's still a good idea to pay very close attention to see which one is which. Time is always independent. The water level is going to be dependent upon how much time has passed. If time freezes, not that that's possible, then the water level is not going to change. It's just going to remain constant wherever it is at that moment in time. So, water level, dependent upon time, which is independent. Increasing versus decreasing. Well, I'm sure you are all familiar with the idea of increasing. As you get older, you increase in height. You increase in responsibility. Some of you are increasing in the amount of homework you have. Things go up. Prices get more expensive. Decreasing. Now, I don't have a long list of decreasings. Hopefully, the amount of time that you spend complaining is decreasing. The amount of time that you spend playing video games will be decreasing. Yeah, we'll stop there. So, when trying to determine if something's increasing or decreasing, we look at a graph and we read it from left to right. So, moving from left to right, what is the line on that graph doing? Well, as I move from left and right, which is a change in my x values that are getting larger, remember 0 is here, so the x now values are getting larger, my y values are going up. That's what causes the graph to increase. So increasing, my x's increase as my y's increase. decreasing. Again, starting at 0, as my x's increase, my y's are decreasing. So a decreasing graph. As my x's increase, my y's decrease. Now that one tends to be a little bit harder of a concept for people to buy, because how can something increase and decrease? It all deals with movement on the graph. The x values are moving to the right, so my independent value is continuing to grow. And because my independent value is continuing to grow, it is having a negative impact on my dependent value. All right, the constant. Now, constant, you'll notice, is remaining the same. So as my independent variable, or my x value, is increasing, my y value has not moved. It has stayed constant. Let's practice. Now we're going to state the change in terms of x values. The common mistake here is to look at this graph and say, hey, the constant is 3. While it's true that the constant has a y value of 3, it is not true that the graph is constant at 3, because we describe increasing, decreasing, and constant based on x values. So generally I will tell students, draw a vertical line through your furthest most left ordered pair, because we're going to read this graph from left to right. And that gives you your starting point. So -5. Well, we are constant at -5. So I'm going to go ahead and label constant. C-O-N-S-T-A-N-T. That's what that says. It's constant from an x of -5 to a x of, well, where does it stop being constant? It stops being constant right here. And from that point, it starts decreasing. But we want to identify that point. So it is constant from x of -5 all the way up until x becomes 2. That's where we start to see a change. Well, the change we have is from this point at 2. So let's change. We are decreasing from x of 2 to x of, well, where did we stop decreasing? Here. That's our value of 3. All right, what happened at 3? I can see that the graph starts going up again. That would be increasing. We're increasing from x of 3 to where? Well, we got to remember what this arrow means. That arrow means the line is going to go on and on and on and on forever and never stop. And since it's going on and on forever and never stopping, we're going to say it's going to infinity. Now, these are your characteristics of functions. Hopefully that should get you well and started into your homework.